Okay, this is section 2.1, day 1, video number 3. So we're going to go through some of the actual application examples here. So example number 5, now that we know that finding the instantaneous rate of change, finding the tangent slope, is the same thing as finding the velocity given a position function. We're going to do example 5. It says, for a particle whose position at time t is given as f of t equals 6t squared minus 4t plus 1 feet, find the average velocity over each time of these intervals of time. So we're just finding average velocities here. So that means we need to do, over the time interval from t equals 1 to t equals 4, we need to do f of 4 minus f of 1 over 4 minus 1. So f of 4, after a little bit of work there, is going to give you 81. Is something probably you should be able to do without a calculator. F of 1 you definitely should be able to do without a calculator. That's what, 6 minus 4 plus 1, so that's 3 over 3. So that gives us 78 over 3. And that actually is divisible. That equals 26. So 26 feet per second. Per second? I'm not sure what the time is. I'm going to assume seconds. Maybe I'll change it if I find out something different later. All right, the average time from 1 to 2. I'm sorry, average velocity from 1 to 2. So it's f of 2 minus f of 1 over 2 minus 1. Plugging in 2, it's going to be 24 minus 8, 16 plus 1 is 17. F of 1, once again, is 3 over 1, so we get 14 feet per second. Okay. The time interval from 1 to 1.2, hopefully you can see what we're doing here. We're starting to make our time intervals closer and closer to time 1. I'm not going to write out the rest of them. The next one, after you plug this one in, you're going to have to use your calculator probably for that one. Gives you 9.2 feet per second. And then the last one gives us 8.06 feet per second on the time interval from 1 to 1.01. So we're getting really close to 1 at this point. Hopefully you can see the trend going from 26 to 14 to 9.2 to 8.06. If you weren't sure about the trend, you could always go to 1.001 and see what you think is going to happen there. But ultimately, I think you can probably estimate that this thing is getting closer and closer to a certain value. Well, we can obviously do it numerically like that, but now we have an exact method. We can actually find the instantaneous velocity of the particle at t equals 1 second. You can pick one of either one of the methods. It doesn't matter. I've used one more than the other one, so I think I'll go with the limit as t approaches 1 of f of x minus f of a over x minus a. As a matter of fact, let me rewrite that t is approaching a. I'll put it in general. That's the formula I'm going to use. Now I'll replace a with 1. So f of x was 6x squared, if I'm not mistaken, 6x squared minus 4x plus 1. And then f of a is what you get when you plug 1 into that, and that would be, let's see here, plugging 1 in, oh, that was 3. We did that several times. Over x minus 3. All right. So we can simplify our numerator. We get 6x squared minus 4x minus 2 over x minus 3. Okay, I can factor a 2 out of the, oops, forgot limit. I can factor a 2 out of that numerator. 3x squared minus 2x minus 1 over x minus 3. And again, we're hoping to get an x minus 3 as a factor. Why do I keep writing x minus 3? It should be x minus 1. Hopefully you guys caught that. A value is 1. I knew something didn't look right, but okay. So now let's see. Now we want a factor of x minus 1 on top instead. So I'm hoping that we can get an x minus 1 out of that, which means that it's going to have to be a 3x. That's how I'll get the 3x squared, and a 1 here, and it's going to have to be a plus. Double checking that. The outside is 1x. The inside is negative 3x. Adding those together gives me the negative 2x for the middle. We're good. So now the x minus 1s will cancel out. Divide those things out to 1. So now we're going to get 2 times 3x plus 1. If I directly substitute the 1 in, we get 2 times 3 plus 1 is 4. We get 8. And more than likely, that's pretty much what I would think that you probably would have guessed numerically on the previous page as we approached 1. This is now the exact way of being able to do it. All right, example number 6. So it says Patrick is driving along a freeway. At 3 o'clock, he passes mile marker 120, and at 5 o'clock, he passes mile marker 250. What was his average velocity during that time interval? So again, average velocity. It's just change of distance over change of time. So let's see, the distance was 250 minus 120. That's the change of distance over the change of time from 5 to, or from 3 to 5. So that's going to be 130 divided by 2. So it looks like 65 miles per hour was his average velocity. Then it says when Patrick passed mile marker 162, he saw that his speedometer read 54 miles per hour. What does the 54 represent? Well, if you think about it, he's passing a mile marker, he looks right down at his speedometer, and right at that instant, hint, hint, he sees that his speedometer says 54 miles per hour. So at that instant, that is the instantaneous velocity. So that is the instantaneous velocity at mile 162 is 54 miles per hour. So the instantaneous velocity at mile marker 162 is 54 miles per hour at that one instant. However, his average was 65 miles per hour over that 2-hour period. Okay. One more example. This has kind of become one of my favorite examples to do, only because it actually makes me realize how dumb I really was when I was doing this stuff in my own classes. And I'll explain that at the end. So example number 7. A sandbag is dropped from a hot air balloon that's hovering at a height of 512 feet above the ground. If air resistance is disregarded, then the distance, s of t, from the ground to the sandbag after t seconds is given by the formula s of t equals negative 16t squared plus 512. So remember, that is your position. Then it says, find the velocity of the sandbag at time t equals a seconds. All right. So in order to find this at a seconds, we want to find the velocity. We need to use one of our formulas. It doesn't really matter which one. I am going to preferably use the t approaching a approach. So we're going to do the limit as t approaches a. We could have used the limit as h approaches 0 and done it that way. We would have just had to have foiled an a plus h. Wouldn't have been a big deal. We could have done it either way. Pick whichever one's easiest for you. So in this case, our f of x, or in this case, s of t, is negative 16t squared plus 512 minus f of a. Now we have to plug a into the original function. Okay, well, it's not going to simplify just to a nice number, so it's negative 16a squared plus 512 all over t minus a. Well, the nice thing is we're going to get a little bit of simplification on top pretty quickly. Limit as t approaches a. So I'm going to get a 512 and a minus 512, so those are going to go away. These things are going to go away. Excuse me, and then be careful. You're going to have negative 16t squared, but you're going to have minus 16a squared, which is plus 16a squared over t minus a. Okay, I've got a 16 in common on the top, and as a matter of fact, because I want to put the negative in the middle, I could either reorder those, or I can factor out a negative 16. So I'm going to go ahead and factor a negative 16 and pull that all the way out to the front of the limit as one of the properties of limits that says we can do that, and pull a constant out to the front. That's going to leave me with t squared minus a squared over t minus a. So this is good because t squared minus a squared is the difference of squares. That can then be factored. So I'm going to get t minus a, t plus a over t minus a. The t minus a's are going to divide out, and that's going to leave negative 16 limit as t approaches a of t plus a. Now remember, a is just it's a number in this case. It's a value of a second. So t is really the variable, and t is approaching a. So I'm going to plug a in for t, because now I've gotten rid of the denominator where there's going to be no more problems of discontinuity. So we're going to get negative 16 and a plus a. A plus a, of course, is 2a, so really what we're going to get is negative 32a. So that is the velocity at a seconds. And let's see, this is in feet and seconds, so that's going to be feet per second. And the nice thing about doing it this way is that now, if I want to find out the velocity at any specific time, I can just plug that time in for a. Well, of course, number 4 here is asking us to find the velocity at t equals 2 seconds. So my velocity at t equals 2 seconds is going to be negative 32 times 2, just substituting the 2 in for the a, because the a represents the number of seconds in this case. So we're going to get negative 64 feet per second. You might ask the question, does that make sense? Can velocity be negative? And the answer is yes, velocity can be negative. Velocity is what they call a vector. It actually has direction to it. A negative velocity does not mean you are moving a negative amount of speed. It just means you're moving that specific speed in a certain direction. So typically we're going to call the negative direction the down direction. Typically we'll call also a left direction a negative direction, just like you would on an XY plane. So typically down and left are negative, up and right are positive. So the fact that this thing is falling makes sense. It's going towards the ground at negative 64 feet per second at 2 seconds. All right, so here's the part where I realized how dumb I really was. I wanted to know what the velocity is the instant this thing strikes the ground, this bag strikes the ground. Well, silly me, I used to think, well, if you drop something and it hits the ground, it's got 0 feet per second. It's not moving. Well, that's true immediately after it hits the ground, but think about this. If you were to, drop something, or hopefully you would never do this, but if you were to jump off of a very tall building and you hit the ground going 0 feet per second, you would never get hurt. Obviously, you have to hit the ground with some velocity. It's immediately after the impact that you come to a very, very quick stop. That's what causes the problems. So in this case, the bag, we want to know what the velocity is the moment it hits the ground. Not after, the moment it hits the ground. Well, if we want to know what the velocity is at the moment it hits the ground, we need to know what time it is that it hits the ground. Well, we have a position function, which is given to us as negative 16t squared plus 512. And if I want to know when this thing hits the ground, I want its position to be 0, no height. So we'll solve this. So if I add the 16t squared to both sides, and then divide 512 by 16, which actually does divide evenly, it's 32. And then we take the square root on both sides. Normally you would put a plus or minus here. The minus has no meaning because that's talking about time in the past. So we're really just talking about the square root of 32. And yes, that can be simplified. I'm not going to worry about it for our purposes right here. But that's the moment it hits the ground. Now I want to know what the velocity is at that time. So I want the velocity at the square root of 32. Plugging that back into our velocity function of negative 32a gives us negative 32 square root of 32 feet per second. Now, of course, if you tell somebody that you're moving at negative 32 square root of 32 feet per second, they're really not going to have much of an idea what you're talking about. So in this case, we'll give a decimal approximation. Plugging that thing into the calculator, we get 181.019 feet per second. Okay, so that's moving pretty fast. All right, there you go. Those are your examples. That is enough for 2.1 day 1. 2.1 day 2 will be a much, much shorter lesson, but we'll finish it off.